Good afternoon, ladies and gentlemen. My name is Jae Jung from Hyundai Motor Company, and it's an honor for me to deliver a presentation in Modelica conference here. Today, I'm going to talk about development of a multi-physical simulation platform for durability prediction for Hyundai and Kia electric vehicles. So this presentation is a one-year project research with an enthusiastic support from Clytex and Dassault Systems. Yeah, let me begin with the presentation. So this is the project background. So not only HKMC, but also most international car OEMs conduct RLDA, which is an abbreviation of Road Low Data Acquisition for durability development. The RLDA is the activity to measure multi-physical signals within instrumented vehicles on predefined proving ground and field conditions. However, in early development stages, when there's no physical prototypes, we are no longer able to conduct RLDA to validate the durability of new mobilities and technologies. Therefore, we want to virtually build all necessary subsystems like this, and then we would like to integrate them into vehicle level to acquire the same signals as RLDA on proving ground and field conditions. So as for XEV point of view, we have defined the possible durability failures not only in conventional mechanical domains, but also in thermal and electrical domains. So as you can see on the right side, we also have defined the list of simulation signals that will be used for further durability analysis. So in this project, the inner motor system is selected as a project target for the most challenging new technologies. So here's the three major features why inner motor system is so challenging. So first of all, inner motor system has 40.9 kilograms heavier than the standard wheel and tire system, and also structurally it gets the direct road impact. And also, the inner motor system is affected both from brake hits and the motor hits in encapsulated conditions, which can cause motor derating or demagnetization. Also, inner motor system requires very complex torque vectoring control logics for also very different driving conditions. So this is the outline of Virtual RLDA. So in this project, we have modeled 6 major systems, such as vehicle controller, hydraulic brake, vehicle dynamics, motor, battery, and thermal management system. And then we integrate them into a vehicle level for Virtual RLDA. So from next pages, I'm going to talk about how each 6 systems are modeled and then validated with the measurements. So the first system is the vehicle controller. So the main role for vehicle controller is to generate driving torque and regenerative braking torque, and also hydraulic brake pressures during the driving. So especially for the regenerative braking torque, it consists of braking regenerative torque and also coast regenerative torque, and it distributed the motor torque between front and rear. So as you can see on the right side, the vehicle controller is built with the DMOLA based on the VCU and IAV control logics. So this is the validation results of motor torque and hydraulic brake pressures. As you can see, for 2 different scenarios. And then as you can see, as for the front and rear motor torque, the driving torque, which is a positive, and then regenerative torque, which is minus torque, can be quite validated with the measurements, as you can see. So it means the vehicle controller is quite rigidly modeled, even for very severe durability scenarios. Our next system is hydraulic brake. So we also have modeled both for mechanical and thermal brake model here. So first of all, when it comes to this mechanical brake model, it takes brake pressures calculated from the vehicle controller that I mentioned earlier as an input. Then it calculates brake torque, as you can see on the right side. When it comes to the thermal brake model, we also have modeled both for standard brake model and also for the 19 inches inner motor rear brake model using thermal network model, considering also conduction, convection, and radiation during the driving. So on the right side, you can check the validation results of both front and rear brake model, and even on the very severe downhill conditions measured in Korea field. So next system is vehicle dynamics. So HMC is using Adam's car as a standard multi-value dynamics model at the moment, and then most vehicle parameters are distributed in Excel format. Therefore, we have built the Excel template-based automatic multi-value dynamics model migration environment to be able to use HMC's standard Adams car model in Demola environment. And also, in order for the efficient simulation, we also have built the automatic preload setting functions according to all different vehicle weight conditions for kinematic and compliance elements. So this is the validation results of Ioniq 5 suspension model with the virtual test rig. So as you can see on the right side, when it comes to the vehicle spring displacement, John's bumper forces, and lower control arms A bushings longitudinal forces are quite well validated with the measurements. And also by modeling all HKMC suspension template model like this, so now we are able to simulate any types of vehicles in HMC in different suspension configurations, whether there is a bushings or not. So next system is motor system. So the left image is the inner motor system in HMC, but due to the confidentiality issues, I'm not able to show the exact schematic of it. But we have modeled both for electrical and thermal motor model here. So as you can see on the right bottom side, so when it comes to the electrical motor model, it's basically table-based model. And then it calculates the heat losses on major heat sources in the motor. And also when it comes to the thermal motor model, it simulates temperatures on major heat sources in the motor model using 1D lumped parameter thermal network model. So the biggest advantages of this 1D lumped parameter thermal network is to represent multi-axial heat transfers within 1D environment. So inner motor system consists of several subsystem models like this, and then all these subsystem models are separately built, and then it will be interconnected within the inner motor model. This is the validation results of inner motor systems, and in both scenarios, the brake pedals are not applied, which means there's only motor's heat effect is applied to see the exact the inner motors heat effect. So in both scenarios, we can see we have validated the winding temperatures compared to the measurements. So next system is battery system, and likewise we have also modeled both for electrical and thermal battery model. When it comes to the electrical battery model, it's modeled as 2 RC based equivalent circuit model. And when it comes to thermal battery model, each surfaces of the battery cell is modeled with different thermal conductivities to represent internal heat transfers. So Using the battery cell model, we can expand it into a battery pack model, using also with the cold plate. So on the right side, this is the validation results of battery pack model on very dynamic vehicle scenarios measured on the Nürburgring circuit. Last system is the thermal management system. Thermal management system consists of three big loops, which are power electric loop. It consists of a motor, inverter, and so on, and also the battery loop, and also AC loop, which is air conditioner loop with the cabin model. So thermal management system model is required to control the motor and battery temperatures during the vehicle driving. So we have validated the motor and battery coolant temperatures on both two different scenarios during the driving conditions. For the durability point of view, vehicle level simulations can be categorized into suspension and powertrain perspective. So this is the standardization of different fidelities of subsystem models depending on different purpose of the simulation. This is the driver and durability scenario modeling required for the vehicle level simulation. And we have categorized the driver and durability scenario models dependent on the type of simulation. So this is the layout of integrated vehicle level model for Ioniq 5 with two rear inner motor systems. In this model, three different modelical libraries are integrated in one big vehicle model. First of all, suspension, drive line, brake, driver, road, tire, and vehicle templates. We use Clitex's Benjamin libraries, which are blue box. And when it comes to motor, inverter, battery, we have used the Dassault Systems EPTL and battery libraries, which is green box. When it comes to thermal management system, we used the TLK's T library, which is red box. So from these pages, I'm going to show you the vehicle level validation results for durability scenarios. So first scenario is go and stop using Ioniq 5's two-wheel drive model. So when the vehicle rapidly goes and stops, then we can see there is an accurate motor torque is generated, and then it distributed the load transfers from between front and rear. So as a result, it results in the correct suspension's reactions like this. So this is the go and stop validation results. Sorry, it takes some time. Sorry. Okay. Next scenario is the Belgian pave. So we also used the Ioniq 5's two-wheel drive model here. So in this case, we have used the scanned Belgian pave surfaces in CRG format together with the F-tire model, along with the very high fidelity of suspension model. So as you can see, the Vegemaf vehicle can simulate very high fidelity of multi-body dynamic simulation. So third durability scenario is impact road. So in this case, we have used Ioniq 5 all-wheel drive model, which means there's two separate motors for front and rear, with also all-wheel drive vehicle controller model. So when the vehicle accelerates wide open throttle, each motor mountings gets the reactive torque due to the motor's local behavior. Also, when the vehicle hits the impact bar, which is red bar in the animation, then the motor mountings also get some damages due to the road roughnesses. So this model can show the realistic behaviors of motor mounting systems, considering the coupled dynamics between a powertrain's local behavior and also together with the road roughnesses. This is the last durability scenario, and in this case, we have used Ioniq 5 with 2 rear in-wheel motors. So during the driving, the in-wheel motor's speed and torques are generated, and then it makes the in-wheel motors heated up. So we can simulate this in-wheel motors winding temperatures like this. And also for some major points of the in-wheel motor systems. Not only the in-wheel motor's temperature, but also we can simulate the battery and brake temperatures at the same time in the simulation. So now is the conclusion. So from this project, we have defined the simulation systems and signals first, and also we've done the system level modeling and validation, such as vehicle controller, hydraulic brake, vehicle dynamics, motor system, battery system, and thermal management system altogether. And then we've done also vehicle level integration and durability simulation scenario and driver modeling. And also using real measurement data, we've done the vehicle model validation. And also from that, we finally developed a scalable virtual RLDA platform. So using virtual RLDA platform, we are going to use this platform model for durability development in Hyundai and Kia vehicle in early development stages. So yeah, this is my end of my presentation, and I'd like to express my sincere gratitude to Clytex and Dassault Systems for supporting our projects. Yeah, thank you very much for listening, and if you guys have any questions, please feel free to ask.